Okay, so I've got two examples left to wrap up this section on linear functions, lines, whatever you want to call them. So the first asks us to write an equation for a line, but we're not given sort of the point and slope information or the pair of points information so we can come up with a slope. We're given an equation for another line, and we're told we want a line that's parallel to it that passes through the point 1, 1. So we want a line parallel to, and maybe double check and make sure I get this right, 3x plus 2y equals 6. And we want it to go through the point 1, 1. So coming back to what we talked about before, we want, as you said, we need a point and a slope. Come on, camera, focus back. Come with me. All right. Hold on a sec. It refocused the instant I pressed pause. That's really aggravating, camera. Okay, so we want a line parallel to this through that point. We've got the point. We need the slope. We can get the slope of this line, and if we want something parallel, then we just need to use that exact same slope, right? So we'll do the same routine that we've done in the previous problem. Let's get y by itself so we have the slope-intercept form, and we can extract the slope accordingly. Subtract over the 3x. 2y equals negative 3x plus 6. From here, divide both sides by 2. Y equals negative 3 halves x. 6 divided by 2 is 3. Not that that part really matters for our purposes, because the thing we really need is that guy right there. That's the slope we're after. So now we've got our point, we've got our slope, and we can plug the point and the slope into our point-slope form. So we have y minus 1 equals negative 3 halves times x minus 1. If you want to do the algebra to rearrange it into the slope-intercept, you'd get y equals negative 3 halves x plus 5 halves. If you're not specifically asked for slope-intercept, it's okay. Just leave it in the point slope. But the slope-intercept, like I said, is the one I kind of like. We'll see kind of why when we talk about graphing in the next section. But all right. So again, this isn't on the notes. I'm freewheeling a little bit here. But what if we wanted a perpendicular line instead? So if we'd wanted everything else the same, basically just kind of imagine marking out that word parallel and writing perpendicular instead. We use the same point, 1, 1, but we need the negative reciprocal of that slope we extracted before. So instead of just using negative 3 halves, if you want to get really specific, 1 over negative 1 over negative 3 halves. That might be a little intimidating, having like this double-decker fraction thing. It's okay. If you just think about flipping over the fraction, it's fine. But the negatives cancel. 1 over 3 halves, it just kind of flips over. And we get positive 2/3 for our slope. All right. Now we can lather, rinse, repeat. We have y minus 1 equals positive 2/3 times x minus 1. And again, if you wanted to dig in, so we have y equals 2/3 x minus 2/3 plus 1. Should get, again, I don't particularly require, at least I just like the slope-intercept. But yeah, you should end up getting 2/3 x plus 1/3. So yeah, that covers that guy right there. All right, so we've talked about the perpendicular and parallel conjunction and how they line up with slopes. So there's one example left, and it's actually a little bit more intricate, or a more involved example of something that we saw back in the first section. So if you read through the problem, again, I'm taking for granted you've got the notes file handy. It talks about the depreciation of a piece of property. We did one of these problems in the first section, but in that particular spot, we were just given the formula. Now we've got to build up the formula ourselves and figure. Then we're basically developing a formula to hand off to somebody else to say when's the value equal to this oddly specific number. All right. So we kind of need to do a couple of things here. There's a few ways you could play around with it, but we're told that the property is initially worth $990,000, and they're assuming that 360 months later, it's totally depreciated. So total depreciation means that it now has a value of 0. So we're basically being given the intercepts in this case. So we know if x is our number of months, so when x is equal to 0, y equals 990,000. So we also were told that 360 months later, the building is worthless is valueless, I guess I should say. So we have a pair of points, 0, 990,000, 360, 0. So now we can build the slope formula in. So then our slope is going to look like the following. So we have y2 minus y1. I'm just using this as my y2. If you had the other way around, that's also fine. 0 minus 990,000 over x2 minus x1. Again, remember, it doesn't really matter which one is x2 and which one is x1, so long as you make sure guys are lined up. We have y0, x360, they're together. y990, x0, that's that guy right there. All right, so now you work out the arithmetic here. You can kind of just ignore the zeros, and you have negative 990,000 over 360. If you work that out, I got negative 2750. All right, so now we want to build the actual, as you say, it says the depreciation schedule or formula. So now we can use the slope intercept or use the point slope form with either of these points. I'm going to use this one because it's already going to have y by itself. So y minus 0 is nothing, equals negative 2750 times x minus 360. You might also prefer to do it the other way so you don't have the parentheses. Like I said, either way works, but the fact that you've got a 0 in either case makes this pretty straightforward to work out. If you arrange it into, as you say, if you distribute the negative 2750, which I'd like you to do in most instances, you'd have negative 2750x, and it turns out 360 times this guy, that's exactly what we came up with there. So, and that should be a plus 990,000. I wrote it as a minus, it should be a plus, because you have a negative times a negative, so you get a positive out of that. All right, so there's your depreciation schedule. So the final thing in the, as you say in this particular section, it says, interpret the slope of this thing as a rate of change. And so the basic idea there is we're kind of writing a sentence. So it's kind of, like I said, a rise over run thing. So the idea is each month that passes, because the months are our measurements of x, right? So, and it measures the change in y, which in this case is the value of our property. So I wrote drops. You could use decreases if you want to sound more financial. But yeah, the basic idea for that sentence there is the following. Each month that passes, our building is worth $2,750 less for, this doesn't say it's for tax purposes like the last one did, so maybe it's like actual value, but that's, what we've got for linear functions. We've taken this depreciation schedule, we extracted the slope of negative 2750, and interpreted that as a rate of change of our value, our property's value as months of time go by. All right, so that's linear functions. So this may not have been a lot of new stuff for you. That's okay. Again, it doesn't hurt to have a refresher on these sorts of things. Linear functions come up in a lot of places. They're particularly important. All right, so next time we're going to take a look at graphing and graphing tools and how to use them. So I won't actually be on a board next time. I'll just be like talking to my computer. So look forward to that if my face bothers you.